Can make a formal start in about 2 minutes. I have the questions on the shared screen anyway if we're going to make an early start. In about 2 minutes, though, we will go through this in a bit more detail. Okay, so good morning, everybody. Today we'll be looking at the following questions. As usual, I'll be around to help out as well. Okay, so the first thing to do is to look at your lecture notes, or you could use Google, etc., to write down a definition, or your definition in own words as much as you can, for what random access machine means. Then we look at the complexity element, explain what we mean by FFN is in big O of G of n, FFN is on big omega of G of n, and FFN is the same as theta of n, using graphs, first of all, and then using definitions. Okay, so you've got to think about again, you're looking at lecture notes, or alternatively, if you prefer to do so, you can use Google, etc. But the point is you have to kind of think about what it means in terms of complexity. So is it it's asymptotic behavior of functions? So you've got to think about whether it is greater than FFN, same as FFN, less than FFN. So is it upper bound? Is it a lower bound? Is it a best estimate, etc.? Okay, so once you have done that, we'll be going into induction. So I'll give you around probably 15 to 20 minutes to try and do the complexity section to begin with. If you have finished the complexity sections, as usual, you can skip forward and go at your own pace. However, complexity, as I think I briefly mentioned last week, when we talked about the problem-solving questions we're doing, we're trying to find out whether an algorithm is good, whether a pseudocode or a solution is good enough. We can use the ideas of complexity to help us. Okay, so first of all, we'll be looking at what random access machine means, and then secondly, big O, big theta, and so big omega and theta mean in terms of upper, lower bounds. Okay, once you have done that, question 3, given that FFN is 3n squared minus 100n plus 6, establish if any of the following are true and why. So is it in the order of n squared? Is it order big O of n cubed? Is order of big O n, or is it or is it big theta of n squared? Okay, so if you've got any problems or questions or queries, the first section, please let me know. Okay, but first of all, this find differential random access machine is relatively simple. Okay, as a reminder, we're looking at, first of all, what random access machine means and what is meant by big O, big omega, and theta notations in terms of upper and lower bounds. It's good. I always think when we do this notation complexities, it's a good idea to think about upper and lower bounds, what it actually is, before we start looking at formal definitions. And yeah, and then once you've done that, to look at question 3. If you've got any questions or queries, you get stuck, please put it in the chat as usual. As I said before, question 1 should be relatively straightforward. It's just finding out what the definition of random access machine is. Okay, so for question 1, find the definition of random access machine. A random access machine is a hypothetical computer with some assumptions attached to it, which are that each simple operation takes one time step, and you count simple operations as addition, multiplication, subtraction, equals, if statement, a quarter, another routine. Also, we consider loops and subroutines as not simple operations. They're composed of many single-step operations. And each memory access takes exactly one time step. So we see we have as much memory as required, and we ignore whether an item is in cache or on the disk. And with this random access machine model, we can measure the runtime of an algorithm by counting the number of steps taken on a given problem. We can assume the random access model machine executes a given number of steps per second, and the count operation corresponds easy to actual runtime. Sorry. So the random access machine, we are not looking at the time for each individual step. We are counting simple steps and then put them together. Okay, so we need this idea when we look at our complexity. Because when we look at complexity, the whole point of looking at big O notation and complexity of algorithms, because you don't care what machine it's on. We don't want to think about what machine it's on, because obviously some machines are quicker, some machines are slower. Whereas with the random access machine model, we can just assume that effectively each step is instantaneous. So we are counting the steps we are taking in that algorithm, rather than thinking about actually the hardware aspects of that. Okay, so normally they are proportional to each other. So once we have given our, say for example, we've got an algorithm n squared, technically speaking, it could take 3 times that or 5 times that, but it'd be proportional to that runtime. Once you've done that, please have a go at question 2. Looking at the complexity notation, and please write in the chat how are you getting on as well, because it's hard to know when we are online how you're getting on. Okay, so please make sure you are using the chat facilities, even if it's just to say I've done question 1, I'm on question 2, because that helps me gauge where you're at. So before, please let me know once you finish question 1 in the chat. So before we start looking at question 2, again, you can list lecture notes and internet to help you, but think about the graphs and then the definitions. Okay, so when you do question 2, just to help you out with the big O notation, if I was going to draw a graph for big O, you'd have your axes. So you have your axes, for example, like that. And then you might have a graph representing your complexity. So it could be, for example, something like that. That could be your FFN, so that represents your complexity of the graph. If I've got a graph which has big O notation, so you're looking at big O of FFN, and you say that's G of N, it's in that, then my G of N, so this kind of thing in the middle, to make it actually got FFN there, so this thing in the middle, use the right notation, so we've got a graph of FFN, so G of N would be a graph which long term, so it could start off smaller than that, but long term it'll be bigger. Okay, so maybe not to begin with, but when you look at over a length of time, because you look at asymptotic behavior, so you're looking at things as they progress forward, and then you get that sort of behavior. So as a formal definition, we have f of x is equal to the order of g of x if you can find a function, effectively, g of x, where k times g of x is bigger than your f of x, okay? So you're looking for this is the upper bound, so you can probably tell. So you've got a value k. You normally say it's a natural number. It's a positive natural number. So you've got this value k, which is just a natural number, and you're saying if I times this function f of n, if I times this function g of n by this, it'd be bigger than f of n. So if I think, for example, if I have the function f of n is equal to n plus 3, if I let g of n be also equal to n, because if I have, say, for example, 3 times n, that's going to be bigger than n plus 3 for n bigger than 2 in this case. Okay, so you're looking at where, for example, the cutoff point here, this now is always bigger than f of n, so it's asymptotically bigger than f of n. So you have to do the same for big theta, which is a lower bound in this case, and then so big omega, which is a lower bound, then theta, which bounds it upper and lower bound by using graphs and definition. Okay, so we have about just over 15 minutes to go to the end. Hopefully you have completed most of question 2 and on to question 3. If you have finished the complexity and you're on induction, just bear in mind as well, we've got another tutorial this week, so if we haven't finished, we'll be finishing off that tutorial. After let's look at induction. When you use mathematical induction, you first of all write down your base case. So, well, before that, even you write down what you're trying to solve, but first kind of step for induction is your base case, then your inductive hypothesis. So, for example, assume K to be true, P of K to be true, and then start looking at P of K plus 1. Once you have written down the induction hypothesis, you prove the inductive step, use the inductive hypothesis, and then you write your conclusion down. Okay, so after you have completed question, the complexity part, we start looking at induction, and then we look at recursion. Okay, so the first inductive questions are to show that the formulae for a handshake problem in the type panel may be established by induction. Okay, so using the principles of mathematical induction, which is important in the functional languages because it links to recursion, how we can formulate it. Okay, so if you have finished the first section of complexity, start having a look at the second section. I'll go through some of the other answers in a few minutes as well for complexity, but as before, please let me know how you're getting on. So we have about 10 minutes left. For big theta notation, share screen instead. So before big theta notation has it's a lower bound. So you're looking at a value of k, which ensures that f of n long-term as again, as before, looking at long-term behavior, is so a constant times a function is less than the function you are looking at. I'm not going to keep this on the screen for too long because I do want to do it independently, so this is a good check or good use it as hints to help you if you're stuck. Theta notation. As I said before, you're kind of bounding your function between a lower bound and upper bound. So technically speaking, it's your big O for your upper bound and your big omega for your lower bound put together. It's the last two put together. Once you've drawn those graphs, you can start looking at the definitions. So as I said before, f, if it's big O, you're looking for a function times k. It's an upper bound on f of x. So looking for all of n greater than a initial value. F of n is less than equal to k times g of n. Big theta is a lower bound. So you're looking for a number which makes it bigger, so less than your original function. F of x equals theta of g of x is an upper and lower bound. So you've got a number times this function. G of x is a lower bound, another number times the g of x is an upper bound. So you probably can alternatively note, which makes an easier definition. It's these first two definitions combined. So f of x is big theta of g of x if and only if f of x is O of g of x and f of x is also theta of g of x. We look at question 3 to establish whether the following 4 statements are true. You can think about the formal definitions. Alternatively, you can think about it in a different way as well. So, for example, A, f of n is order of n squared, big O of n squared. This is true because I have an n squared which dominates n and the constant 6. So, because n squared dominates, I could have, for example, 4n squared, and that would be bigger at some point than minus 100n plus 6 added onto the 3n squared. Okay, so, but what I should do is, when we do this, establish whether it's true. So you look at these ideas, but then when it says y, you have to use the formal definition. So think for constant, multiplied by it, which becomes greater than for the first 3 and less than for the last one. So before we've got 7 minutes left, if you've got any questions, please put it in the chat. Okay, about 1 minute left, so I'm going to quickly go through question 3 to finish off the session. So for this function, 3n squared minus 100n plus 6 is an order of n squared, like I said before. If you have a value of 3n squared minus 100n plus than 6, that is less than 3n squared plus minus 100n plus 6n, which is less than 3n squared minus 64n, and again 3n squared. So hence 3n squared minus 100n plus 6 is less than or equal to 3n squared for all of n greater than 4, so we can pick k as a 4. And this is not unique, we can have k as 3, it's not unique, we can have 4, 5, etc. as well. B is also true, because again, we can pick a value. In this case, we can just pick a value, so we can just pick, for example, k is equal to 3 for n cubed, and we get the same solution. For C, this is false. You can clearly quite see that 3n squared grows bigger at a faster rate than n. If 3n squared minus 100n plus 6 is order of n, then it exists a case such that all n bigger than n. And we pick kn greater than or equal to 3n squared minus 100n plus 6, and then basically disprove this, and hence it's not an order of n. Question 4, it's also true because we can pick 2 as our n squared for a k. Again, it's not necessarily unique, we can have possibly 1. And we find that 2n squared is less than or equal to 3n squared minus 100n plus 6 for n greater than 100. So again, this would be true. Okay, so this concludes today's tutorial. You can sign out now whilst I put you get ready for the next tutorial. So thanks for coming along, and I'll see you the next session I have with you.